All right, let's dive right in. Today, we're going to talk about a fundamental law of physics. And I mean, this thing governs everything that moves. We're talking rockets blasting into orbit, sure, but also something as simple as you taking a walk. It's this constant, invisible push and pull dance that's happening literally all around us all the time. So, to really get a feel for this, let's start with a little puzzle. Imagine this, right? You've got a sailor standing in a small boat right next to a dock. He takes a leap forward to land on the dock, but the moment he jumps, the boat shoots backward. What's going on there? It's not magic, that's for sure. It's pure physics. Well, the answer to that little boat puzzle, it comes from one of the most elegant and honestly powerful rules of the universe, something Isaac Newton figured out centuries ago. We're talking about his third law of motion. And there it is, so simple, right? To every action, there is an equal and opposite reaction. I mean, that one little sentence explains, well, pretty much everything about how things move. What it's really telling us is that forces are never lonely. They don't exist by themselves. They always come in pairs. Physicists have a name for this, of course. They call it an action-reaction pair. And this pair has a few simple rules. First, the two forces are always the same size, perfectly equal. Second, they always point in opposite directions. But here's the absolute key, the part you really got to lock in. They always act on two different things. Okay, so what does this actually look like in the real world? Because this isn't just some abstract idea from a dusty old textbook. Nope. Once you know what you're looking for, I promise, you are going to start seeing these force pairs absolutely everywhere. Let's break down a few examples. Let's start with something you do without even thinking about it, walking. Now, you probably think that to walk forward, you push yourself forward. Makes sense, right? Well, it's not quite right. The action is actually your foot pushing the ground backward. And the reaction, that's the ground pushing your foot forward with the exact same amount of force. Yeah, let that sink in for a second. The road is literally pushing you forward. Every single step you take, it's planet Earth giving you a shove. Without that reaction force, you'd just be running in place. It's this amazing little partnership between you and the ground beneath your feet. Okay, how about a more dramatic example? Firing a gun. The gun pushes on the bullet with this huge forward force. That's our action. But at the very same moment, the bullet is pushing back on the gun with an equally huge backward force. And that backward push, yeah, that's the recoil. And this whole push-pull dance, it's everywhere. Think about two football players colliding. It might look like one hits harder, but nope, the forces are identical. A rocket launching into space is like the ultimate example of the third law. The rocket pushes super hot gas down, that's the action, and the gas pushes the rocket up, that's the reaction that sends it to the stars. You can even see it with something as simple as two spring scales pulling on each other. They'll always show the exact same reading. Always. Okay, so right about now you might be thinking, wait a minute. There's a question that pops up here that trips up almost everyone. It feels like a paradox, but trust me, once you see the answer, the whole thing just clicks. The question is this. If the forces are always equal and opposite, why doesn't everything just cancel out? Why isn't it always a tie? I mean, if I push on a wall and the wall pushes back on me with the same force, shouldn't it just be a big fat zero? Why does anything move at all? And here is the secret, the key that unlocks the whole thing. The forces don't cancel out because they are acting on different objects. Think about it. One force is on the wall, the other force is on you. Forces can only cancel each other out if they're both acting on the very same thing. If you take one thing away from this, let it be this. It's so, so important. Okay, that makes sense. But it kind of leads to another puzzle, doesn't it? If the forces are always equal, why aren't the results equal? And the answer to that one comes down to a single word: mass. Yeah, let's go back to that gun. We've established that the force pushing the bullet forward is exactly the same as the force pushing the gun backward. So how come the tiny bullet zips off at incredible speed while the big, heavy gun just gives a little kick? Let's break it down. When it comes to the force, it's a tie. It's equal for both. But then we look at mass, and that's where everything changes. The bullet has a super low mass. The gun has a really high mass. So when you apply that same equal force to both, the low-mass bullet gets a huge acceleration, and the high-mass gun gets a very low acceleration. It's that simple. And this is such a perfect illustration of the big idea here. The effect of a force depends completely on the mass of the thing it's acting on. You can have the exact same push, but if you apply it to a pebble, it's going to fly. Apply it to a boulder and, well, it's barely going to move. Same force, totally different results. All right, so we've gone from boats to bullets to just walking down the street. Let's wrap all this up and boil it down to the key things you really need to remember. So here's Newton's third law in a nutshell. First, forces always come in pairs, action and reaction. You can never have just one. Second, these two forces are always equal in strength and opposite in direction. Third, and this is the big one, they act on two different objects, which is why they don't just cancel out. And finally, the amount something accelerates from that force, that all depends on its mass. That's the whole dance, right there. And I'll leave you with a little something to chew on. Imagine two kids on separate little carts with wheels. One kid throws a heavy bag over to the other. Now, using everything we've just talked about, what happens to the first kid's cart at the exact moment they throw the bag? And then, what happens to the second kid's cart when they catch it? Think about the push and the pull. The answer is all in there.